today is Rankeya Datta, and the title of the talk is Uniform Approximation of Abhyankar Valuation Ideas in Mixed Characteristics.
Thank you. I'd like to thank the organizers for organizing this wonderful celebration. Karen, it's a joy to celebrate you and your contributions to mathematics. And thank you for giving me an excuse to eat cake 3 times a week already this time. And as you will see, the tradition of eating cake with Karen goes a ways back. I think it was about 10 years ago that I approached you somewhat nervously to see if you were interested in working with me. And you responded by asking me if I wanted to think about valuation rings. And at that time, I think the only thing I knew about valuation rings was that they were highly non-Noetherian. So your question made me more internally nervous, but your enthusiasm for these objects was really contagious. So contagious that I've still been thinking about them 10 years later. And I am happy that I'm able to say something new about these objects that you love today. And to put my talk in context, soon after their amazing theorem about symbolic power ideals, Ein, Lazarsfeld-Smith proved another equally astonishing uniform approximation result for valuation ideals of certain classes of valuations that arise commonly in geometry. Their result was in equal characteristic 0. The goal of today's talk is to discuss a mixed characteristic analog of the result of Ein.
What about characteristic P?
That was my thesis. So I will get to that. So the goal today is again to discuss
That's
a mixed
true, actually, now that you say it.
characteristic.
Well, you skipped that detail, sorry.
All right,
Wait.
so throughout today, F is going to be a field, and W is going to denote a valuation from F to gamma, which is a totally ordered abelian group. So, i.e., what do I mean by this? So W is a group map where gamma is an ordered abelian group such that the valuation of the sum of 2 elements is bigger than or equal to the minimum, the valuation of x, and the valuation of y. Associated with the valuation is the valuation ring, which I'll denote by OW. And the valuation ring is the set of non-zero elements in the field whose value is non-negative, and I'll also include 0. The valuation ring turns out to be a local ring, and the unique maximal ideal can be nicely described as well. This is just the set of elements, non-zero elements in the field F, whose value is strictly positive, and we include 0 again. I will denote the residue field of this local ring by K sub W. So this is OW over NW. And I'm going to denote the image of the group homomorphism, which is also called the value group of the valuation, by gamma sub W. This is just the image of this valuation. This is called the value group. The rational rank of the valuation is just the rational rank of the value group. Is just the dimension over the rationals, Q tensor. Some more terminology. So I'll fix the domain A and a prime ideal Q in the domain. And we're going to say that the valuation W is centered on the pair A comma Q, maybe this is a non-standard definition, if the following conditions are all satisfied. So I'm going to require that my centers today are all Noetherian. So A is Noetherian. And moreover, I'm going to require that the diffraction field of A is the ambient field of the valuation. The second condition is that A is contained in the valuation ring. And since I have this prime Q lurking around in the definition, the way this comes into play is that the maximal ideal of the valuation intersected with A gives you Q. Another way to think about condition 2, i.e., is that the local ring OW dominates the localization of A at Q. So the starting point of my talk is the following fundamental result due to Abhyankar from the 50s. So this result is characteristic independent. And the theorem says that if W is centered on AQ, then this implies that the rational rank of W plus the transcendence degree of the residue field of the valuation over the residue field at Q is always less than or equal to the height of A at Q. So now comes the central notion of today's talk. So we'll say that A comma Q is an Abhyankar center of the valuation W if equality holds in the above inequality. This notion is fundamental enough for me in today's talk, but I'll also put it on the board just so that you all remember. If the rational rank of W, the transcendence degree of the residue field over the rest of the valuation over the set residue field of Q is equal to the height of. Let's discuss some examples of valuations that satisfy equality with respect to a center. So the first one is kind of silly. If your value group is isomorphic to the integers, then hopefully you know that the valuation ring itself is a DVR, it's Noetherian, and is an Abhyankar center of W, quite trivially. And my definition of a center is that it has to be Noetherian, but in this case, the valuation ring itself is Noetherian. So equality is satisfied because you always have the inequality. So in this case, this rational rank is 1. It's always bounded above. And in this case, the center is just OW itself, which is dimension 1. So equality has to hold. So let's do another example where the value group is the integers, but this example is less trivial. So suppose f is a function field over a ground field small k. This just means that f is a finitely generated extension of a field small k. And let's suppose that w is trivial on the ground field. What does this mean? This just means that k is contained in the valuation ring, or equivalently, when you restrict the valuation to the non-zero elements of k, you get the trivial group. I'm going to let x be a normal model of f over k. I'm going to let E be a prime divisor on X, and let's assume that W is given by the order of vanishing along the divisor E. Then, as is well known, this implies that the value group is isomorphic to Z, and in this case, the valuation ring O sub W is Noetherian. Locally, it's the localization of a normal finitely generated algebra over K at a height 1 prime. So you get also that the transcendence degree of the residue field of the valuation of the ground field is 1 less than the transcendence degree of the function field over K. Now here's an observation. Suppose that your W is centered on a finitely generated K algebra. Let's call it A sub K, A comma K. So let's think about what the dimension of A localized at Q is by the dimension formula. This is the dimension of A, which in this case is the transcendence degree of F over K, because A is a finitely generated K algebra, minus the dimension of A mod Q, which is the transcendence degree of the residue field at Q over K. But now let's substitute the equation from star. So if we do the substitution, this just becomes 1 plus the transcendence degree of Kw over K minus the transcendence degree of the residue field at Q over K. Now 1, because the value group is isomorphic to the integers, is the rational rank of W. And because transcendence degree in towers of field extension is additive, the transcendence degree of Kw over K minus the transcendence degree of the residue field at Q over K is just the transcendence degree of Kw over the residue field at Q. So in other words, therefore, for these valuations arising as order of vanishing along a prime divisor, any finitely generated center is an Abhyankar center. So the way one should think about this Abhyankar center condition is that if a valuation ring admits an Abhyankar center, you should roughly think about it as being a higher rational rank analog of a divisorial valuation. And so far, I've not given you any valuations with rational rank greater than 1, so let's fix that. So we need to start. Yes.
Question. What kind of properties of the divisor guarantee that A is finally generated?
What kind of properties of the divisor? So, well, I'm just taking a center A. The A does not depend on W here, sorry. I'm just assuming that there is a finitely generated center
Sorry.
for the valuation. Okay. Right. So next, let's discuss a higher rational rank analog, or a higher rational rank example of evaluation with an Abhyankar center. So we should give at least one example of polynomial rings. Karen, and there's talk with Karen in the audience.
I don't know if I've ever really said that.
I don't know. Okay, so we'll fix positive real numbers beta and gamma such that the set 1, beta, and gamma is linearly independent over the rational numbers. So I'm going to let QP be the field of p-adic numbers with associated valuation. I'll just denote V sub p. And now I'm going to define this valuation in a two-step process. So for a polynomial f in 2 variables over q sub p, I'm gonna let W sub beta comma gamma of F be defined to be the minimum of the following sum. Where the coefficients are non-zero. So you can check that this definition satisfies the properties of evaluation but on this domain. So this is not quite a field. So I want to extend it to its fraction field using the usual tricks. So for a fraction f over g now in QP round bracket x over y, we're just going to define the value of f over g as the value of f minus the value of g. And one can check that this gives a valuation of QP round bracket x comma y. But if you're only used to thinking about valuations in the equal characteristic setting, something different is going on here. Namely, if you restrict this valuation to QP, it's not the trivial valuations anymore. You get the p-adic valuation. So W restricted to QP is VP, p-adic valuation. And in this case, it's not that difficult to see that the value group is just the following free abelian group of rank 3 that is sitting inside the real numbers. And it's also clear that W is centered on ZP square bracket x comma y, and the prime ideal is in fact the obvious maximal ideal generated by P, x, and y. So now, since we always have an inequality in due to Abhyankar, so since the rational rank of W plus the transcendence degree of the residue field at W over the FP, which is the residue field of the center. So the residue field here is FT. So since this is always less than or equal to the dimension of this local ring, you see that equality has to hold because the rational rank is 3 and the dimension of this ring is also 3. So equality must hold. So this is a higher rational rank example of a valuation that admits an Abhyankar center. Yes.
Sorry, could you repeat? You said something on the left-hand side was 3. Which
This rational rank
rational
of the
rank.
value is 3 because it's a pre-abelian group of ranks here. Yes.
Okay, yes, that makes sense.
So if I were to define some sort of maybe real rank or something, where instead of using the rational numbers, I use the reals, this would be rank 1.
Absolutely. This is a rank 1 valuation, a real rank.
The real rank is interesting, isn't it?
I'm sorry?
I mean, that is an inherent bonus.
Yeah. Okay. So if you've been following along with my examples, all of my examples have been examples of valuations that are real valued. So that's what we're going to assume from now on. So from now, we're going to assume that W is R valued and non-trivial. So what does this mean again in terms of algebra? Or first, in terms of the value group, this just means that the value group is a non-trivial group and it sits inside. You can embed it inside the real numbers. Or equivalently, this is also the same as saying that the valuation ring has Claude dimension 1. But just bear in mind that unless your value group is isomorphic to the integers, this valuation ring is going to be highly non-trivial. Okay. So if A comma Q is a center of W, So this W is now real value. And for a real number M, I'm gonna let alpha sub M be, as a set, the elements with value at least M, and you throw in 0. If you think about it, this set alpha sub M has the following properties. The first property is that this is an ideal of the center A. The second property is that this equals A if M is less than or equal to 0, because W is centered on A. The third property, because I'm real valued and real numbers have the Archimedean property, is that these ideals are all primary with respect to the center Q. Whenever M is positive. Fourth property is that if I look at the elements with order at least n in A and expand it to A localized at Q, then this will give me the elements of order at least n at A localized at Q. Fifth property is that if I take the product of two of these ideals, then this will lie inside alpha sub M plus M prime, because of just the definition of evaluation. So in particular, this property implies that if I take the valuation ideal of order M and raise it to a non-negative integer L, then this always sits inside the valuation ideal of order L times M. So let's do an example of what these ideals look like for, say, the rank 3 valuation that I just defined using the irrational numbers beta and gamma. So let W sub beta gamma be the rank 3 valuation on the p-adic round bracket xy with center. Now I'm just going to assume that the center is local instead of just taking zp squared bracket xy and just localize it at the maximal ideal. So in this case, you can check that the valuation ideal of order M at the center, I can explicitly describe its generators. It's generated by monomials e to the I, x to the j, y to the k, such that I plus j beta plus k gamma is bigger than or equal to M. This is monomial. This is a monomial ideal in the regular system of parameters. E x y. Okay. So now comes the central question of today's talk, which I'll write on the board. So I'm in this setting of a real value valuation. Question I want to raise is that if your center A is nice, for example, say A is regular, and it's an Abhyankar center of W, then is there a positive real number E such that for all real numbers M and non-negative integers L. So we know from the discussion on right here that the valuation ideal of order L times M contains a power of another valuation ideal. The question is, can I arrange things so that this valuation ideal is also contained in a valuation ideal as power? That's the question. So the E is independent, works uniformly. It's independent of the choice of M and F. Okay, so it's really an invariant of the center. Okay, so this is the question that Karen, Lawrence, and Rob considered in their paper. And so here are some results. The first theorem is that the answer to this question is yes if A is regular and finitely generated over the field of characteristic zero. This is the theorem of Ein-Lazarsfeld-Smith.
Alpha to value means powers of ID.
I'm sorry? Yeah, it's just the ordinary integer power. Yeah. And then in my thesis, I showed that the answer to this question is also yes if A is regular and finitely generated over an F-finite field. Characteristic T. And here's me right after defending my thesis. I should point out that in the published version of my thesis, the theorem is stated only with the assumption that the ground field is perfect, because there were some separability issues that I couldn't quite circumvent, but you can now assume that the result also holds when the ground field is finite by recent work of Dale Kukoski. So you can get rid of the separability issues. But this does not appear, the theorem does not appear in print anywhere in this form. But the methods in my paper just readily adapt to the finite setting once you have Dale's results.
So you're saying using Dale's.
Using Dale's recent work, you can get rid of the separability assumption that I needed.
And what's the reason for assuming the valuations of Abhyankar?
Because this fails if your valuation is not Abhyankar, or does not have an Abhyankar center. Not always, but there exist valuations, and I can give you an example at the end of the talk if you're interested. Yeah. So here is the theorem for Karen's birthday today. So the theorem is that the answer to this question is also yes if A is regular and a finitely generated extension of a DVR of mixed characteristic such that the following two conditions hold. I need to assume that the residue field of the DVR is perfect. It's a perfect field of characteristic.
Can't get rid of that Dale's thing?
Because I need to use the uniformization result of Knopf and Kuhlmann here. And Dale's result is an equal characteristic result, where he removes the hypothesis. And the second, somewhat more annoying assumption that I need to make is, okay, so the DVR is sitting inside A, which is sitting inside the valuation ring. So this quotient, the quotient of the value group, over the copy of Z sitting inside the value group that comes from the DVR is torsion free. Trying to get rid of this assumption, but haven't been able to.
So you don't know an example where you need it?
I don't know an example. Okay. So before I describe the sort of key tools that go in the proof of the mixed characteristic analog of the Ein-Lazarsfeld-Smith theorem, I'd like to mention one corollary of this, of an affirmative answer to this question that may be of independent interest. Corollary typically goes by the name of Izumi's theorem. So the corollary is that when the question that I just raised on the board is affirmative, for A, Q, and W, as in this question. And V is any other R-valued valuation with the same center, then there always exists a positive constant C such that Wx is less than or equal to C times Vx for all non-zero x in the center. So as long as W is nice, doesn't matter what V is, you always get this bound. But so Izumi's theorem is known in in a very general setting by work of Marx Minkowski, and I forget the other author's name right now, and one of his students. But you also get it as an easy consequence of an affirmative answer to this question. Okay, so now let me describe the key tools that go into proving the mixed characteristic version of the uniform approximation result. So we are always going to work over a fixed dVRV of a mixed characteristic 0 of P, such that the residue field is perfect. And then I'm going to assume that A is a regular, finitely generated V algebra extension domain, and Q is a prime ideal of A. It says that Q contracts to the maximal ideal of B. And then I'm going to assume W is a real valued valuation of the fraction field array, such that this quotient group is torsion free. And obviously we'll stick to the setting where the center is a nice center. X comma Q is an Abhyankar center of W. This is going to be my setup for the rest of the talk. So the first free ingredient that helps me prove this result of mixed characteristic is a local monomialization result due to Nath and Kuhlmann. So this result is that there exists always a finitely generated birational extension into B such that B has the following properties. So for this result, you don't need A to be regular. I'm just sticking to the regular case because the question was, or my theorem is one where A is assumed to be regular, but for this result, you don't need A to be regular. So there exists a finitely generated birational extension A to B such that B is regular. W is centered at some prime ideal of B. So far, there's nothing monomial about these two conditions, but then the third condition is that there exists a regular system of parameters x under bar of the local ring of B at Q, such that for all real numbers m bigger than 0, the valuation ideal of order at least m on the center B localized at Q is monomial in this regular system of parameters. And it's in this theorem that we need the hypothesis that this thing is torsion free.
I see.
And that the residue field is perfect because of some separability issues.
Yeah, that was also a problem in your thesis.
Yes.
Yeah, we're having that.
So this is the first key ingredient. So essentially what this allows us to do is reduce the case where your valuation behaves like the beta gamma valuation that I mentioned earlier, rational rank 3. The second key ingredient is the theory of mixed characteristic test ideals that is developed by Barger-Platt, Intron Ma, Joel Patek-Falvey, Carl Schweid, Kevin Tucker, Joe Waldron, and Jakob Wittich. So again, I'm going to give you some definitions in a simple setting, in the setting that I need. Okay, so I'm not going to give you the most general definition of a test ideal, and so on. So my setting is again B is a DBR of mixed characteristics 0, comma P. A over B is a finitely generated regular domain extension of B. And I'm going to let alpha be an ideal inside A, and I'm going to let T be a non-negative rational. So then, the test ideal of the pair A comma alpha with exponent T is the following. So I'll denote the test ideal using this notation. And so my definition is actually a very non-trivial result in their work. So this is a non-trivial theorem because I don't want to talk about perfectoid rings and other things. I'll give you a definition that is maybe similar to parse, but it's a non-trivial result. So it's the image under the trace of x over A. Now I'll mention what I mean by x and everything in a minute, of the push forward of OX of this divisor, epsilon divisor of P. P is just the prime, the residue characteristic of the DBR, T plus epsilon M. So now let me explain what everything means here. So where epsilon is a small positive rational number, and pi from x to spec A is a sufficiently large alteration such that, so you can assume that x is normal, or you can also assume x is regular because you're working over DBR, doesn't matter. You can always dominate any alteration by a regular one in the DBR setting. P to the epsilon is a global section.
You mean by Johan's theorem?
By Johan's theorem.
Okay.
Yeah. P to the epsilon is a global section of x.
That's also our theorem.
M is just alpha OX. You can assume that this is Cartier. And because you're allowed to join algebraic elements of the algebraic closure of A, of the fraction field of A, you can also assume that T plus epsilon times M is Cartier. So my notes say that Carl has something to say about the epsilon.
So the reason we have the epsilon is no one's proved your thesis yet in mixed characteristic, or the final paper, the inventionist paper in the thesis has not been proved in mixed characteristic. So tight closure equals plus closure kind of statements.
That the kernel of some mappable homologies seems
Yeah.
the map to R plus.
Yeah, that's sort of the missing piece. Otherwise all these epsilons would go.
The epsilon looks like a.
It's a test
type of-
element.
Yeah,
It's a test
oh, I
element.
see, yeah.
Okay, so we can also define this test ideal. I'm not going to do it, but we can also define the test ideal for R complete regular local. But instead of defining the test ideal in this setting, let me just give you an example of the case of interest for me. So the example is, suppose R is complete regular local of mixed characteristic. X is a regular system of parameters. X consisting of x1 up to xt is a regular system of parameters of R. And alpha is a monomial ideal in this regular system of parameters. I'm going to let sigma be the convex hull of the D tuples such that this monomial is in my monomial ideal. This is also called the Newton polygon of this monomial ideal. So in this setting, the test ideal of the pair R comma alpha with exponent t is the same, has the same description as in Howell's thesis for multiplier ideals. So it's also generated by monomials, such that lambda bar plus the coordinate vector consisting of all ones is in the interior of t times sigma intersected with your lattice. So this is the same description that works in equal characteristic theorem for multiplier ideals. Okay.
And equal characteristic P for test ideals.
And equal characteristic P for test ideals due to Hara and Yoshida? Yeah, I think so. All right, so the relevant properties of the test ideal for me for today's talk are the following. So again, B is a DBR of mixed characteristics, and I have a regular domain. So I'm assuming A is a regular domain. In their work on test ideals, you don't always have to assume A is regular. So it's much more general than what I'm presenting here. And alpha is an ideal of A. So the first property of test ideals is that there is no confusion about exponents. So if you have a natural number n, then the test ideal of the pair A comma alpha with exponent n times t is the test ideal of the pair A comma alpha to the n with exponent, oops. With exponent t. The second property is that if you have an inclusion of ideals, then you got to also get an inclusion of test ideals. It's inclusion preserving. Third property, you need regular, and you can weaken this to PCM regular. If you know what that means, is that the ideal alpha is contained in the test ideal of the pair A comma alpha with exponent 1. The fourth property is famously called the subadditivity property, which is that the test ideal of A comma alpha with exponent n times t is contained in the nth power of the test ideal of alpha with exponent t. The fifth property is that this test ideal commutes with localization completion, even though I never defined the test ideal of a pair for complete localness. So if Q is a prime ideal of A such that P is contained in Q, then this implies that if you take the test ideal and expand it to the completion of the localization, then you just get the test ideal at the complete level. And the sixth property is that there is a birational transformation rule. If you were interested, I can tell you more precisely what this rule is at the end of the talk. Yes.
So regarding fall, is it true that if I have the test ideal with exponent like t plus t prime that's contained in the product?
T plus t prime.
Yeah, because here it's like t plus t plus t plus
Yes.
t.
Yes. I
You can take
didn't state the most general version of subadditivity. Yeah.
We can even take two different ideas.
Yes, two different
It'll
ideas.
be in the product of the facilities.
Okay. So my theorem was about uniform approximation. I introduced these complicated objects. Why did I do so? Let's just justify this quickly. So you keep the properties. Yes.
So DVR is complete or not?
No. So they got, so this version is not up yet, but the completeness hypothesis is not there anymore.
It's been completely.
Or it's kind of.
It's been completely erased.
That's what we did in Lausanne.
Okay, so now we'll come back to the setting of valuation ideals. So that A will denote the family of valuation ideals, alphas of them. The then ranges over the non-negative reals. And I'm going to fix them. So observe that for two positive integers L and K, if I look at this test ideal, then by property 1, this is equal to this test ideal by property 1. Something wrong?
For large K.
What? No, I just write 1 over L as K times L over
Oh,
K
sorry,
for
yeah.
any K.
Right.
But you have a K in the
So you
subscript
have
too?
a K in the subset.
Oh, sorry. There's
No.
Then you just can contain that.
what is happening? Ah! Wait, what? Ah! Sorry.
Yeah.
Okay, this is correct. Sorry. Thank you.
Okay, that makes sense.
Sorry, Karen. And now by property 2. Okay, so the kth power of the valuation ideal of order, at least Ln, is contained in the valuation ideal of order k times L times m. So by the second property, this is contained here. This is correct, I think. So the upshot, therefore, the upshot is that if you fix an m and look at this collection of ideals, as you let L range over all positive integers, this is directed under inclusion. That's what this above check shows. So now, therefore, if I define what is called the mth asymptotic test ideal of this family, so if I define tau a comma m dot a bullet is the entire family, to be the scary looking sum, and because my ring A is Noetherian, the ideal is finitely generated and the system is directed, this equals the test ideal of the pair for some highly divisible K. So I don't want to introduce terminology officially, but this ideal is called the asymptotic test ideal of order M of the family A bullet. So the asymptotic test ideal of order M satisfies the following properties. So 3 on the left, on the right hand side implies that the valuation ideal of order M is contained in this asymptotic test ideal of order M, because K equals 1 is in that sum. 4, and this is a fun exercise for you to do if you're bored, is that the asymptotic ideal of order L times M of the family is contained in the Lth power of the asymptotic ideal of order M. So this is by the subadditivity property. Okay. Now let's come back to our original question. What are we asking for? We want a positive real number E such that for all non-negative real numbers m and integers, positive integers L, the valuation ideal of order L times m is contained in the Lth power of the valuation ideal of order m minus e. So my claim is that in order to show what we want, it suffices to show that the following infinite intersection of colon ideals is non-zero. So I replace the problem by a seemingly harder problem, maybe. It's an infinite intersection of ideals. But let's just prove this claim very quickly. So suppose I have a non-zero x in this intersection. So wherever does my e come from? My e is just going to be the value of this x. So by definition, x multiplies this asymptotic test ideal into alpha sub m. So by properties of valuation ideals or valuations, this tells you that the asymptotic test ideal of order m must be contained in the valuation ideal of order m minus e. Something here times something here has valuation bigger than or equal to m, means the valuation of this element has to be m minus the valuation of x, which is e. But now we're almost done, so therefore this tells you that the valuation ideal of order Lm by star, this is contained in the asymptotic test ideal of the family of order Lm. But now by star star, this is contained in the Lth power of the asymptotic ideal of order m. So we just saw that the asymptotic ideal of order m is contained in alpha m minus e. This is contained. That's your proof. So if you can show that this infinite intersection of colon ideals is not zero, then your theorem holds. So in the last 5 minutes, I want to illustrate a specific example in which this intersection is not zero. So let's go back to the rank 3 valuation, where you have the p-adic valuation on QP. You send x you give x the value beta and y the value gamma, where beta, gamma, and 1 are q linearly independent. Okay. Now this is my A, this is my Q. So I need to produce an element in the intersection here. So I claim that P times X times Y is actually in this intersection. Since all my ideals are primary with respect to the center Q, I can check this claim after localizing and completing it. Check. Claim after passing to the completion of A localized at Q. But let's just recall what the valuation ideals are. They're monomial in the system of parameters P, X, Y. So the valuation ideal of order M expanded to this completion is generated by P to the alpha A1, X to the A2, Y to the A3, where A1 plus A2 beta plus A3 gamma is at least M. That's the valuation ideal expanded to the completion of the localization. And now you're going to fix a highly divisible integer L such that this asymptotic test ideal of order M of the entire family expanded to the completion is the test ideal of the pair A comma alpha sub Ln with exponent 1 over L. Which, because test ideals commute with localization, completion, and localization is also the test ideal of this pair. But now in the complete local setting, we have a good description of test ideals and monomial ideals. And the center is regular local, so let's apply the Newton polygon example. So, but this test ideal is equal to the ideal generated by the monomials in Pxy such that v1 plus 1 comma v2 plus 1 comma v3 plus 1 is in the interior of 1 over L times sigma intersected with the lattice D, where 1 over L sigma is the convex hull of the points A1 comma L, A2 comma L, A3 comma L, such that PA1 times x to the A2 times y to the A3 is in the valuation ideal of order L times m. By playing around with what does it mean for this monomial to be in this ideal? It just means that A1 over L plus A2 over L plus A3 over L is at least n. And I just, so A1, oh sorry, there are betas. Betas. Again. Is that okay? All right. So I have a point which is a convex linear combination of points whose coordinates satisfy this inequality. So the coordinates of this point must also satisfy the same inequality because it's a convex linear combination. So this implies that v1 plus 1 plus v2 plus 1 beta plus v3 plus 1 gamma is also m. But let's translate this inequality to a condition of monomials. This is just saying p times x times y times p to the p1, x to the p2, y to the p3 is in the valuation ideal over n expanded condition. Okay. Pxy multiplies every generator of the test ideal into this valuation ideal. So it multiplies the entire test ideal into this valuation ideal. This implies so the intersection does indeed contain p times x times. Okay, so I'd like to stop here, but before I end my talk, I'd like to thank Karen for being a wonderful advisor. And it's really been a pleasure working with you over the years. Thank you very much for everything.
Thank you, wonderful student.
So you need a regularity for subadditivity and for that claim.
I need the regularity for subadditivity and
for the proof of that claim.
For the proof of that claim. This claim?
Yeah, previous.
For the previous claim. Yes, I need subadditivity in the previous claim. So that's where the ID is regular.
Okay, but do you think so? You really need a regularity for that claim?
I don't know how to get this without regularity.
Yeah, but
this claim might hold more generally, but I don't.
Yeah, that's correct. Yeah.
Maybe this holds more generally, and then they'll give you more general instances where the question has an affirmative answer. But the proof that I can give you needs regular because of subactivity.
Then it is counterexamples if you don't assume regularity.
You can counter examples if you don't assume that the center is Abhyankar. Can I give you counter examples if you don't assume
And I do not think that
regularity?
there exists.
I don't know. Maybe there doesn't. There probably doesn't. So in equal characteristic 0, Carol Bloom proved a slight generalization of the original result of Ein-Lazarsfeld-Smith, where instead of this containment, there's a twist and an L power of the Jacobian. And I think you can do the same trick in prime characteristic. Oh, so this is when A is assumed not to be regular but KLT. And I think in prime characteristic, you can do the same trick by replacing regular by strongly irregular. And then you have to make a twist by the power of the Jacobian. I haven't worked out the details, but I suspect this also holds.
It's like an adaptation of our proof. I mean, this is kind of our proof, but then how Mel and Craig adapted it.
Yeah.
For the symbolic powers.
But I don't know if you can get this without assuming A is regular, if that is the question that was being asked.
Where do you use that portion-free hypothesis?
In the local normalization result. So the birational transformation law lets me reduce the case where valuation ideals are monomial with respect to a regular system of parameters. So I can apply all of this.
Right.
But that to apply that such a monomial center exists, I need the torsion-free.
But the local normalization is not known, I guess, without that hypothesis.
Without that hypothesis in mixed characteristic.
But it might be true.
It might be true.
When you say nice, more than regular, you require it to be finitely generated over a period. Like what?
That's the setting in which I can prove the theorem.
So nice.
Nice. It is today for today's talk. Nice and regular.
More questions?
Okay, thank you.